Okay, so we'll start now. Okay, so last time we have started chapter 2, which is on multiple integrals, right? So what we are trying to do is to consider a function of two variables, which is a curved surface, right? And then we consider the space underneath this curved surface, right? And then we want to find out the volume of that space, right? So over some rectangular boundary, right? So and to do that, we realize that actually all we were trying to do is to do the integration twice. Okay, so basically now we have these two layers of integrals, right? We take care of the inner integral first, and then we do the outer integral. Okay. And last time we were focusing on the case where the boundary is always a rectangle, right? So this time we'll look at a more general situation where the boundary are described by curves, okay, instead of just four straight lines forming this rectangle. So first of all, I found a minor typo in this slide. Okay, so the order is reversed. Should be from C to D. Okay, from C to D. Okay. So here, let's look at how do we describe a boundary which is not rectangle. Okay. So again, I'm not drawing the third dimension, right? So you just need to imagine that my my curved surface is somewhere out of the page, right? Somewhere here. So now I want to consider this integration region, okay, D. So you can see that this is no longer a rectangle, okay, given by four straight lines. So instead, what I have, first of all, I still have two straight lines. Okay, the left boundary is represented by this x equals a, and then the right boundary represented by this x equals b. So however, you can see that my upper and the lower are curved. Okay, so and suppose they are described by two functions. Okay, y equals g1 x, and then y equals g2x. So the idea of doing this integration, right, as you can recall from last time, is that we are going to still treat it as like a loaf of bread, right? And then you cut it into many slices. So basically what we are going to do is to cut this region into many slices like this, right? So, and when we consider one of the slices, right, we need to set up the integration limit, right? And that integration limit is determined by the y position of this point, right? That's the lower limit, and then the y position of this the other edge. So before, right, when we have this rectangular region, right? So for every slice, right? So I always start at y equals c, and then stop at y equals d, right? So that's why my inner integrals, right, it's just described by this constant lower and upper limit c and d. However, in this case, you could see that now this lower limit and the upper limit, they will be different for different slices, right? So if I consider a slice over here, right? So then this is my lower limit, this is my upper limit. If I consider this line, right, this is my lower limit, this is my upper limit. So the limits themselves are also changing, right? So that's why when we set up the limit for the inner integral. Okay, so I need to consider the y position, right, at a particular x value. So that's why my lower and upper limits now expressed as a function of x, right, instead of just c and d, two constant. So however, the way that we do integration will still be the same. Okay, so because when we treat the inner integral, in this case, we are integrating with respect to dy, right? So that's why x is just a constant, right? We pretend that x is a constant, right? So that's why even the lower limit and upper limit contain x, you don't need to worry about that. It's still a constant to you, at least in this step. So that after you take care of these steps, right? So again, you find out an expressions which is depending on x, right? So then now you treat it as a function of x and then take care of the outer integral. So again, the same two steps process, right? So, but the outer integral, we can still use two constants as the lower and the upper limit, right? Because the left and right boundary are still defined by just two straight lines in this case. Okay. So now, suppose I consider another case. Okay, this time you can see that my boundary at the top and the bottom, they are straight lines. But this time the boundary on the left and on the right are described by curves. They described by functions. So then this and this, right, are just these two lines, right? And then this curve and this curve are given by these two functions. So again, you might do the same thing, right? So you might be thinking, okay, again, I'll just cut it like this, right? Cut it like this. However, it turns out that if you do it this way, this time it won't be very convenient. Okay, so because you can see that if I consider, for example, this slide, right, then my y limit will be c to d constant. But then if I'm out here, then my upper limit is no longer given by this constant d. So that means you need to kind of further divide this region into a smaller sub-region, right, in order to set up the limits for different regions. Okay, so I'll give you one more example to make it more clear. But anyway, in this case, we will try to cut it along the other direction. Okay, we'll try to cut it along this direction. Okay. So if I cut it along this direction, that means I want to integrate over x first. Okay, so that's why you can see that the inner integral is with respect to dx. And this time, when I take care of the lower and the upper limit for this inner integral, right? So I need to know for a particular y value, what is the x value of this lower edge, and what is the x value for the other edge. Okay. So that's why my inner integral, right, so will be expressed in this form, and then my lower and the upper limit given by these two functions. So this times, after I evaluate the inner integral, I'll get a function of y, right, instead of function of x, and then I take care of the outer integral, right? So this time the outer integral is given by two constant limit again because of this straight line and this straight line, right? So let me give you one more example, okay, to actually tell you how the function looks like. So let me just add one blank slide. So suppose my integration region is given like this. Okay, suppose again, this is my XY plane. Okay, so I want to have this sine curve here. I have a sine curve here. So in fact, this is y equals, it's a shifted sine curve, right? So sine x plus 2, let's say. So that means this is 2. And then this would be pi, and then this would be 2 pi. So now suppose I want to have an integration region over here. So suppose this is my integration region. So in this case, how will you cut this region? Will you cut it vertically or horizontally? So which one is more convenient? Right. So vertically is more convenient. So if we do it horizontally, too much. If you do it this way, okay. So what you realize is that for all these slides, right? So your limit is always going from 0 to pi. But then when you're up here, so then you actually need to find these two values, right? Using this curve here. So that means if you are actually going to try to do it the horizontal way, you need to divide the whole thing into two sub-regions, right? So the first one is this rectangular one, and then the second one is the one that goes up top here. So similar situation goes here, right? So if I'm going to consider the integration to be this part here, again, you want to cut it vertically, right? So again, if you cut it horizontally, you get something even worse. But for this part, you have to have this small slice here disconnected with the other small slice here. Okay. So, but anyway, there are only two typically. So, we'll just either do it vertically or horizontally. You just need to look at the geometry to pick the one that is more convenient in your problem. So now let's try to see this example problem here. Again, I'm considering a this plane, right, which you have seen in the last lecture, right? So a very simple function, and then again, I'm going to consider the volume of the space underneath this plane. But this time, my integration region is a triangle like this. Okay. So that means if I try to draw it here, my integration region is triangle like this. Okay. So then this time you have to again take care of the limit more carefully, right? So, and it turns out that for this case, right, so you could see from the geometry that no matter you cut it vertically or horizontally, okay, the calculation should be almost equally convenient. Okay. So if we indeed try to cut the slice horizontally, right? So what you have for the inner integral, right, is that your lower limit is y, right? Because this line is y equals x, right? So that means for a particular x value, right? So this is equals to y. So then this is your inner integral, right? So you, after you integrate it, right? So you get a function of y, and then you take care of the outer integral, get a number. So if you do it the other way, right? So this time I cut it vertically. So that means I need to do the integration with respect to y first. Okay. But notice that this time, okay, you can see the difference is that my limit, right, go from the lower limit is 0, upper limit is x, right? So the key is to identify these two different. Make sure that you understand why you have these two limits here, but here you have these two limits here. So that at the end, of course, you get the same answer. So a slightly more difficult example. Okay, this time I have this curve, and then the region, okay, looks like this. So if I want to draw it on the same picture, right? So basically, it is this straight line, and then I have another, which is a parabola. I want to take this region, okay. So right here is clear enough, right? So you can see the two intersection point between the parabola, right? So and this y equals x straight line. So if I want to find out the volume under this surface, right? So in this picture, I cut it horizontally, right? So that's why I need to take care of the integration with respect to x first, okay? And then you have to express, right? So your lower and the upper limit, okay, in terms of y. Okay. So that after you complete the inner integral, where you get a function of y, and then for the outer integral, I just get from 0 to this y value here, which is just 1. So you can try by yourself on how to evaluate the integration, right, by reversing the order. Reversing the order meaning that I need to cut it the other way. I want to cut it vertically. So I'll just give you the answer, but you can check to make sure that you understand this. Okay. So again, make sure that you understand the difference between these two limits and these two limits. Okay, so now let's move on to another coordinate system. Okay, so we have been doing this Cartesian coordinates or rectangular coordinates. So now we are going to do another coordinate system, which is known as the polar coordinate system. So let me make one more slide. So I actually assume that most of you have seen polar coordinate before, but here just a quick review, right? So again, let me draw the XYZ space. Right, so this is my curved surface. So of course, for every point in the XY plane, I can use this pair of coordinates. So here, if I just draw the XY plane one more time, so this is my point X, Y. So now in polar coordinate system, right? So we're using another pair of variables to represent the position of this point. Right, so the two variables that we use in polar coordinate is, first of all, is the distance from the origin to your point, right, which we call r. The other is the angle between this dashed line and the x-axis, so which is this theta. Right. So that means for any points in the xy plane, right? So we can either use xy or r theta to locate that point. So then, suppose I have this function of x and y. So then, of course, I can also express it as f of r and theta. So then, basically, what we are going to do in the followings is that we are going to do integration with respect to the r and theta variable, okay, instead of doing the integration with respect to the x and y variable. So remember when we do Cartesian coordinates, we have this grid, right? This rectangular grid, right? So in which each small section, right? So the area of this small section, right? So this dA, which we call the differential area element, is given by this dx times dy. So how do we form this grid? Right, it's easy, right? So basically, first of all, we take a line, right? This x equals a, which represent a fixed value of x, right? And then we move this line a little bit to the left, a little bit to the right, right? So by a distance dx, and then we repeat the process again, right? So to form a set of vertical lines, right? The spacing is dx, and then similarly, right? So we have this horizontal line, and then it's y equals c, and then we move it up a little bit by a distance dy, and then do it again and again, and then we form a set of horizontal line. Right? So at the end, we have this rectangular grid. Right? So basically, from one line to another, you are changing one of the variables by a little bit, right? It's either dx or dy. So now, instead of changing dx or changing x or changing y, right? So we are talking about changing r and changing theta. So first of all, if I have this plane, so still the horizontal axis will be x and the vertical axis will be y. But here, if I'm talking about not a fixed value of x, not a fixed value of y, but I'm talking about a fixed value of r. If I tell you I am at a point where r is some number. So if I tell you that I'm at a point where r equals a is just some constant, then that actually not talking about a straight line in this xy plane. Okay. Instead, it's talking about this circular arc, right? Because every point on this circular arc, right, has the distance a from the origin of the coordinate system. So this r equals a is given by this r. Or you can actually draw a full circle, right? A circle of radius a, right, is centered at the origin, is represented by r equals a. So now if you move out a little bit, right, so basically I'm saying r equals a plus dr, then you are now here, right? So you are at a circular arc which has a slightly larger radius. So then you draw, you keep the same process, but you keep drawing bigger and bigger circles. Okay, so they are all concentric circles, right, centered at the 0, 0, 0. So then I have this set of lines, right? They are not straight, they are all circular arcs. So then now let's take care of it, the other variable, theta. Okay. So for theta, if I am at a fixed value of theta, right, if I tell you that I'm at theta equals alpha, then basically that means I'm on this line, okay, where the angle between this line and the x-axis is alpha. So now if I add d theta, so if you are at theta equals alpha plus d theta, then you are on the next line, okay, which has a slightly steeper slope, right? But still, this line has to, if you extrapolate this line, it has to pass through the origin of the coordinate system. Okay. So then you just keep doing this. You draw many of these lines diverging out from the origin point. Then at the end, again, you have a grid, but you see that it's not really rectangular like this. So now if I want to look at just one small section of this grid, right? So I take it out. So if I want to calculate the area, so we know that, well, you can see that from this picture, it's not exactly a rectangle anymore, but since it's small enough that we could just assume that the area is just approximately given by the product of this side and this side. Okay. So the length of this side, of course, is dr. Okay. And then the length of this side, okay, is r d theta, okay, this small, very short circular arc, which is close to a straight line. So then that's why my differential area element, dA, is given by r times dr d theta. So notice that, okay, so no longer the product of the differential of the first variable and the second variable. It's not just dr d theta, it's r times dr d theta. Okay. So now, if we want to calculate the integral, right, of course, we also need to express my function in x and y in function of r and theta, right? But that's the other thing, and that should also be straightforward. But also we need to take care of the integration limits, right? So here we have the integration limits using x variable and y variable as the reference, right? But here we are talking about limit for the r variable and the limit for the theta variable. So from this picture, you can clearly see that if I have this constant lower limit and upper limit a, b for r, and then this constant lower limit and upper limit for this theta, the boundary that you construct, right, is no longer a rectangle like this, right? Instead, is this kind of shape. So in principle, what if I still want to do the integration, okay, over a rectangular boundary, right, but in polar coordinate system, right? In that case, so that means I still want to have a boundary like this. Okay, I want to consider this region, but I want to do it in polar coordinate. In principle, you can, but now you have to express these four lines in polar coordinate first, because right, neither of these lines represent r equals to a constant, right, nor theta equals to a constant. So that means that the basically the idea is that if you are doing polar coordinate integration, then basically you are not considering this kind of region. If you are considering this kind of rectangular region, it's probably more convenient to go back to Cartesian coordinate. So then when will it be convenient to use polar coordinate, right? So here we consider some typical boundary. My circles are all missing. Okay, I'll draw them out again. So suppose I want to integrate over a circular region. Okay, this circle of radius b. So I want to have this region. So again, you could imagine that you can do it using Cartesian coordinate, right? But you need to express this function carefully first, right? So you need to take care of the changing upper and lower limit as a function of x or as a function of y. However, if I want to consider this circular region, right, using polar coordinate is much more convenient. So all I need to do is, first of all, right, so to describe the outer boundary of this this region, right, basically I just use r equals b, right, just r equals b. Basically, it's the radius. And then what about the lower limit? Because I'm including everything inside, so then you just need to imagine that you have this another circle of radius 0, right, sitting at the origin. Then so that means that there's just effectively nothing there. So that's why your lower limit is from 0, right, all the way to b. So now what about the theta limit? Right. So to consider, if you go back to this picture here, right? So if I consider from theta to alpha to theta to beta, right? So basically, I'm considering the region bounded by these two lines, this line and this line. But here I'm considering a full circle, right? So that's why if I take my first line to be a horizontal line, right, exactly overlapping with the x-axis, then basically, so that means that I have this theta equals 0. So now you imagine that you sweep this line. So you rotate this line, so to let it sweep across the circle. I just keep moving, right? So keep moving until it finish sweeping across the entire region of the circle, right? So then that's why my second line is theta equals 2 pi. So then if you want to integrate over a circular region, you see that is very convenient to do it in polar coordinate, because you're still dealing with constant lower and upper limit. So now if I want to consider this case here, so this I no longer have the 0 to B, but I'm going from A to B, right? So R equals A is a smaller circle. So suppose A is smaller than B, right? So then I draw two circles. So one is this, and the other is a bigger one. So from A to B, that means that I am considering the region bounded by the two concentric circles. Okay. But again, whether I'm considering the full region or just part of the region has to be determined by the theta limit. Right? Again, my theta limit is going from 0 to 2 pi. So that means I'm considering a line, and then I just let it sweep across the entire circle. So that's why in this case, I'm considering a donut shape of region. So finally, this one, for this one, again, I go from 0 to B. Right, so that means, again, I have to draw a circle like this. But this time, I go from 0 just to some theta naught. Right? Suppose theta naught is just some small angle. So then that means this is my starting line, and then this is my ending line. Then what I'm considering is the region for just like a slice of the pizza. Okay. So this is how we take care of the integration region in polar coordinate. Okay. Right. So that's similar question as what I just said, is that if I want to consider a rectangular region or a elliptical region or any other region that you can think of, is that again the idea will still be that you need to express that function in polar coordinates. Okay. As long as you do that, then that's fine. Right? So you can imagine that if I want to consider this ellipse, right? So you need to somehow express this R as a function of theta, right, to represent this ellipse. Then, of course, if you are considering a full ellipse, then clearly you are going from 0 to 2 pi. So that one you don't need to worry about. But then for the R limit, so you are going from 0 to f of theta. Right? And then f of theta has to be a function that represents your ellipse. You need to figure out how to express an ellipse in polar coordinate. Maybe you have learned that before. So again, an example. Okay, same function over again, but this time I want to integrate over a region of a quarter circle. Okay, this quarter circle represented by this function here. Right. So first, again, just to remind you that of course we can still use Cartesian coordinates, right? Because you could imagine that we can still cut the slice like this, right? You do that. Basically, this is the integral that you obtain, right? So again, this integral itself is not I'm not going to actually do the integrals now. So I just want to make sure that you understand how to set the limit. Okay. So now in polar coordinates, right? So if I set the limit, right? Basically now, as you know, you are considering this type of region. You're considering this type of region. And from 0 to this line, so this is a pi over 2. So that's why your integration limit, right, just from 0 to the radius, and then from 0 to pi over 2. So one more example. So this Gaussian function with two variables, something you have seen in the last chapter, but here I want to do the integration, right, over a circular region, right, on the xy plane. So again, if you try to use Cartesian coordinates, right, so what you're doing is to cutting this circle into these slices, right? If you are thinking of this, then this is the integral that you'll get. So, but then here I run into this trouble. Okay, I not able to integrate this. Cannot express it in any elementary function. Okay. So now let's consider the same problem, but in polar coordinate. Okay. First of all, if I need to transform this function into this form, okay, and then first nice thing you can see is that, okay, so here I have the function of two variables, but then effectively here I just have one function of one variable now. But anyway, so I need to put this function into my integral, right? And then because I'm integrating over a full circular region, so that's why my r limit is from 0 to the radius, right? My theta limit is from 0 to 2 pi. So there's one nice thing here, because you can see that the inner integral, or the inner integral, has nothing to do with theta, right? So after you, no matter what your answer is for the inner integral, but theta won't show up, right? So that's why you can basically take this whole thing, right, outside the outer integral. So that is, it can be treated as a product of two integrals. So you can see that the first one is something that you find trivial. Okay, so but let's take the second one now. So now we realize that we are able to express the second integral as elementary function. Right? Instead of integrating this Gaussian function, we are integrating this Gaussian function times the variable r. Okay. So that's, and because of that, because I have this r extra factor r here, I'm able to do a substitution of variable or change of variable, okay, to make it this integral of this exponential function, right, instead of integral of and Gaussian function. So integrating an exponential function, of course, we know how to do. Okay, so then at the end, I have this. So in fact, in the previous example, okay, so we are considering a function that does not depend on theta. Okay, just a function of r. So I believe you see this kind of functions again and again, and we'll say that, right? So this system has cylindrical symmetry, right? So that means the fact that it does not depend on theta means that even you rotate the whole thing by any degree, right? So the function looks the same. So that's why this function does not depend on theta. And in fact, you see that in this case, effectively, right? So this double integral can always be written in a simple form in this single integral. It's just that the integral for d theta gives you a factor of 2 pi. So now if I look at this 2 pi r dr, it actually has a geometric meaning. Okay, so this 2 pi r dr is in fact the area of a very narrow circular ring. I just consider this is my whole integration region, and then this is one of the small, one of the very narrow circular ring in this region. Right, so the thickness of this ring, or the width of this ring, is dr. So that means when you are doing this kind of integral, that means you're cutting the integration region into many concentric rings. Right, so just like this. Right. So but again, if your function actually depends on data, right? So this is not what you can do. Okay, here let's take since we lost some time already, so but still let's take a 5-minute break. We'll come back at 12:35. Okay. Okay, so let's continue. So now I believe we are familiar with the standard procedures for calculating a double integral, right? So, and geometrically, we understand that that's refer to the volume of some space right underneath a curved surface, right? So that's the geometric meaning. So now we want to put it in the context of physics. Okay, so in physics, when do we need to use the technique of double integrals, or later even triple integrals? Right? So, and physically, we need that when we are doing a sum, right? Or when we are doing some kind of average, we need to sum over many small elements. Okay. So the first one. So from your mechanics class, I believe you have learned the concept of center of mass. Right. So let's make it simple. So instead of considering a 3-dimensional space, so let's consider just the particles. They are all in the 2-dimensional plane. Okay, the XY plane. So suppose I have n particles, right, distributed in this XY plane. Okay, and so by definition, the coordinates for the center of mass of this system of particles, which I denote the center of mass coordinate to be x bar and y bar. Right, so it's given by these two formulas. That's the formula for finding the center of mass position. So now, suppose I want to consider, instead of discrete point particles, I want to consider some mass, right? So distributed across some continuous region, right? Just like a plate, a plane, a plate, right? So a plate, again, a plate lying on the XY axis only. I don't consider the thickness of this plate. Just assume that this plate has no thickness. So then this is the shape of my plate, suppose, and then and also suppose the mass density, okay, at different region of the plate have some variation. Right? So in that case, I will need to use a function, a function rho, as a function of x and y, to describe the mass density of this plate, right? So at different points, right? So in this case, right, because we are considering this continuous distribution instead of this discrete point particles, so you can imagine that for every small region, right, dx dy, I will have a tiny bit of mass. Right? So that then when we want to find the coordinate for the center of mass, right, I need to do the double integral. So here, instead of summing over the mass of each particle times its x coordinates, so I'm summing, right? So the mass of a small region dx dy is given by rho times dx dy, right? So that's the tiny bit of mass in that region, right? And then times the x coordinate of that region, and then divided by the denominator is just the total mass of your plate. So same idea, go for the y variable. Okay. So then this is a example here. So what I have is that I have this region R. Okay, so this blue region, suppose is the shape of my plate. Okay, and I make it simple. Suppose this blue region, the plate, has a uniform density, just rho naught. So that means every point on this plate have the same density. So if I go ahead and use the formula I showed you in the last slide, right? So this is what I need to do. Then because rho is just a constant, right? So it makes things easier. So now if I consider this is considering the denominator. Okay, so this is finding the total mass, right? The total mass of this plate. So you can see what I'm doing. So I'm actually, am I cutting it vertically or horizontally? So I'm doing it vertically. Right, so I'm cutting it like this. So then for each vertical slide, right, start at 0, end at square root x. Okay. So then of course for the other limit, just go from 0 to 9. So then this integral is just well, straightforward enough. So now I also need to take care of the numerator, but again you'll see that the integral is also straightforward. So that at the end, right? So I just need to find x bar. I need to take this number, right? Divide by this number. To find a y bar, I need to divide this number by this number. So then this is the answer here. So you can try to locate this point, right? It must be a point somewhere inside this region R. Okay, so another example. This is, I believe this is an example that you will see again in your 2041 course. Okay, I guess in your 2041 you are not yet learning E&M yet, but let's just try to get a taste of this kind of problem. Okay, you'll see it again. So what I consider is the following. Okay, so I have a circular plate. Okay, again, I'm just ignoring the thickness of this plate. Okay, so and then this circular plate is positively charged. Okay, And then this is lying on the XY plane, and then it's centered at the 0, 0. So suppose I am here. So I am at a vertical distance h above the plane of this plate. And then when I look down, I'm looking down exactly at the center of the plate. Okay, so I'm still I'm still at the point which is lie on the center axis of this plate. So I'm here. So what I want to find out is the electric field at this point. Okay. Or you could imagine that is the electrostatic, is the repulsive force that you experience at that point. Okay. So the assumption is that okay, I already tell you that I assume that there's no thickness, and then I assume that the charge is uniformly distributed across the plate. Okay, so there are many charges in this plate, but the charge density is uniform across the entire plate. And then I just let the total charge, the total amount of charge, be this capital Q. Okay. So how do I find the electric field at this point? So I assume that you have learned Coulomb's law, okay, at least for 1 point charge. Okay, so if you are just considering the 2 point charge, 2 point charges repelling each other, that would be easy, right? So if you are here and then there's a point charge here, right? So then you know that at your point, the electric field due to this small point charge, right, will be given by this formula. Right. At least this is something that you know already, just for 1 point charge. And this d squared, just the d means the distance between this point charge and yourself, and then this d hat vector is just a point charge that goes along this line, right? So, but now that's the problem, is that I don't have 1 point charge. I have many charges on this plate, right? Basically, you need to consider the charges at all the small regions on the plate, right? And then you calculate the electric field due to every small region, and then do a sum. And in principle, you also understand this is a vector sum, right? Because if the charge here is pushing you to this way, and then if you have another charge here is pushing you this way. Now, the net effect of the 2 charges is that you experience an electric field that's something like this. But now I'm talking about so many points on this plate. Okay, so however, there's one thing that's nice is that we don't actually need to worry about the vector nature of this electric field, because at the end of the day, you will, by the argument of symmetry, you understand that the final result is that the electric field must be pointing in the z direction. Okay. So if you are exactly on the axis, okay, if you are away from the axis, that's another much more complicated story. If you are here, then if you are here or there, then of course the electric field will have this x and y component. So, but why is it? Why do we only have the z direction for the field, right? So one way to think about is that, as I said, symmetry, right? So suppose my final answer tells me that the total electric field point to this way. If this is my final answer. So then if I rotate the whole system by some arbitrary degree, for example, if I rotate the whole system by 180 degrees, then you tell me that no, the electric field is pointing to this way. But before rotation and after rotation, you are considering the exact same electric field plate, the same plate. Then it's not possible for you to get two different answers. So that's why it must be only possible answer is that the total electric field due to the entire plate is pointing up. So that's the argument using symmetry. But if you want to look at it in more detail, in a more microscopic way, where you could imagine that whenever I consider a small region, maybe somewhere here, and then you'll receive the electric field like this. You can always find a complementary part of this on this plate, which is canceling your horizontal component. Right, so you add up this and this, you must be getting electric field that just go up. And if I take this region where you get a electric field that's kind of go into the page like this, but you can always find a complementary part plate which is giving you an electric field pointing kind of out of the page. So at the end, so all I'm saying is that you just need to add up the Z component of every tiny part of the plate, right? And then sum them up. And here you could imagine that the sum is not using this discrete sum, but using integration. Moreover, since we are considering this circular object, it's not surprising to you that we are going to use polar coordinates. So to do that, so I'm considering a small area element, right? So on this plate, right? So this looks familiar, right? So the dA, the differential area element, expressed in polar coordinate, RD theta. So that in this small region, so I have some tiny amount of charge, which is dA times the charge density. So what is the charge density? Charge density I just write here is this sigma, and that's simple. The sigma is just the capital Q, right, divided by the entire area of this plate. But anyway, sigma is just a constant. So then you can see that I have this. This is the small amount of charge that's present in this small region. And then I have, of course, I have this factor 1 divided by 4 pi epsilon naught, right? So, and then I have to consider this distance here, right? The length of this red dashed line, d. I need to know d squared. And also at the end, as I said, I only care about the Z component, right? So this would be the electric field dE due to this small region, right? But at the end, I just need to know the Z component of dE. So that's why I pick this factor of cosine alpha. Okay. So now, with just some manipulation, is that I'm just going to express cosine alpha as h divided by d. Okay, so at the end, I have everything expressed in terms of h or d, but no this angle alpha. So then this is the contribution from this tiny area. So next, we do the double integral. Okay. So the double integral, how to set the integration limit. So I'm considering a full solid circle region, right? Then of course my R limit is going from 0 to the radius of this plate. And since it's a full circle, then of course I go from 0 to 2 pi for the theta. So then this is the integral that I need to solve. Okay, so this I suppose you know that this one requires just a simple substitution. Okay, so then this is the result that you get. So here is an interesting question there for yourself to think about. Okay, to consider two limiting cases. Okay. First, okay, the easier one is actually this one is R tends to 0. So when R tends to 0, you understand that it just basically behaves like a point charge. So that means you expect that if you take this R tends to 0 limit, you get back the simple 1 over h squared. Right? So here is not 1 over h squared. You can see this looks more complicated, but when you take the limit, that's one thing you expect, right? 1 divided by h squared. That's the electric field due to one point charge. So another thing that you can think about is when you have R tends to infinity. So an infinitely large plate. I believe so. For this case, again, you learn it in your E&M class, and in fact, for that one, you also use another method to calculate the electric field, which is known as the Gauss law. So in chapter 3, in this course, we'll also say a few words about Gauss law when we learn the flux and the divergence theorem. Okay, so yes.
What is interval all of this? You can integrate the uniform charge. You get the center of charge, the center of mass. You get the center of charge and that there is one charge and then you get the electric field from driving up to the H point. Height of H.
So that's a good question. So first of all, ask yourself, what is the center of mass of this plate? Where is the center of mass? Just here. So if I just basically imagine that is equivalent to, so all the plate, all the charge in the plate concentrated at the origin. If you imagine that, what result would you get? It's just 1 over h squared, and that's different from this. Okay. So that's a good question. Okay, so you can think about another example, which I believe you learned in your E&M class, is that if you I don't consider a plate, I consider another geometry. Let's say a straight long rod. Okay, very straight, a very narrow rod. Again, it's uniformly charged. Okay, uniformly charged. And then again, let's say this is the middle line. Okay, and then I'm standing here. I ask you the same question. I want to calculate the electric field at this point due to this charged wire. So you could mathematically imagine that you can do integration, right? But this is actually easier to do because you just need to. This is a single integral, not a double integral. So at the end, so again, this is, let's say, h, right? And then this electric field. And then you will find electric field, of course, will be some function of h. This is what you will find. Okay, that makes sense. And again, you can ask yourself, what about I treat all the charge in this wire, and then just take the center of mass, and then just imagine that they all equivalent to concentrating all the charges at this point, and then just take this point and this point, and then take the 1/h squared. Again, you'll find that the result is wrong. So, but there is one example that seems to work. Is that if I consider a sphere, a three-dimensional sphere, okay, not just a circular plate, and again, I consider that I'm here, and then I this uniformly charged sphere, and then I want to ask the electric field at that point. Again, you can do an integration. You can imagine that you can, but this is actually a triple integral. Okay, triple integral, not a double integral. So, but still, you can imagine that using the concept of integration, you can add things up and find the electric field. But you realize that this times is actually equivalent to concentrating all the charge at the center of the sphere and just use 1/r squared. In this example, it appears to be equivalent to that. But all I'm saying is that you cannot take it for granted. Okay, you cannot just always say that, oh, okay, because there's center of mass, and then you just imagine that you concentrate all the charge there, treat that as point charge, and then do 1/r squared. Okay. In general, that's not correct. But it just so happened that for the sphere, you do get the correct result. Okay, I won't say much more than that because you learn all this again in your E&M class. Okay. Okay, so we are about to move to triple integral. Okay, but just one more slide before we go there. It's just that so you could imagine that actually if we take one step backward, okay, the concept of double integral, we know that is means the volume under some curved surface. But it can also simply mean the area of the integration region. But because you could imagine that if my function, the curved surface is just one, right? So then this double integral just becomes this, and this is basically the area of this region here. And that actually makes sense because if you don't care about this part, if you just care about this part, I believe this formula is something that you learn in high school. So you know that if I want to find the this area D, this is the formula that you would have used in high school, right? But actually, this you can also express in this form that looks like a double integral. Okay. Okay, so now let's move on to triple integral. Okay. So first of all, for a function of two variables, you are able to draw it, right? A curved surface in three-dimensional space. However, for a function of three variables, okay, difficult to draw. Okay, you could imagine that this will be a function of three variable will be an object that lives in the four-dimensional space, if you want to put it that way. But there's some practical example that we could try to give ourselves some intuition. Is that what is the practical example for three-dimensional the function of three variables? Right? So just consider this room. So suppose there's every part of this room have slightly different temperature. So then if I want to describe the temperature in this room, right? So then I need a function of three variables. Right? I need to give you the XYZ coordinates of a point, and then I tell you that temperature. So temperature in this three-dimensional space in this room can be described as a free variable function. And then you could imagine a mass density, right? So because just now the example I gave you is a plate that has no thickness, right? But if I actually have a three-dimensional object, right, so you need to tell me, which point you are at in that object, and then I tell you the mass density at that point. So then this describe the mass density or even charge density of a three-dimensional object, then you need a function of free variable. So now, suppose I want to evaluate the following. Okay, so now you can see that I have this three-dimensional space here again. Okay, so here, okay, so remember, I'm not drawing any function here. As I said, I have difficulty in drawing this function of free variable. What I'm drawing is an integration region. So previously, I draw a rectangle to be the integration region, right? So in many examples. So here, I draw a box, okay, a rectangular box to be my integration region. Okay, and then to define this box, of course, you need to give me two numbers, two constant number in x, two constant number in y, and then two constant number in z. Right. So now now we are not talking about the differential area element. Okay, so I'm talking about the differential volume element. Okay, so I'm considering a small, tiny box, or tiny, tiny cube, tiny box inside my entire, my big box here. So then the more volume of that, right? So it's given by this delta x times delta y times delta z. So suppose I want to evaluate this quantity. Okay. So at every point, right, I construct this box, and then I want to find out the function value at this region, right? And then I go to the next, the adjacent region, right? Consider the other small box, and then consider the function value at that box, and then do it over and over again, right? So I consider all the small sections, right, in this entire box region, and then sum them up. So to represent this kind of sum in three dimensions, right? So in the continuous limit, right? So we use this triple integral sign. Okay. And perhaps it's not surprising to you that, right? So actually, what we need to do is an integral for 3 times. So before that, when we do double integrals, basically we are talking about an integral that has two layers. Right? So now we have 3. So then here is again give you some geometric intuition, right? So previously we cut it just into slides. Right? So here we need to start from a small rock. Okay, that's for the innermost integral. That is considering along this line, we do the integral for this function. You could imagine that at each point in this line, right? So I have different values for the function. So I need to do this integral. So then the second step, the second layer, that now I figure out one of this bar, small line or small bar, and then I'm considering all the bars in the same layer or the same level. And then after finally, so that means after the second step, I figure out the entire layer of this box, right? And then the last step is that I consider all the layers in this box. So then here is the summary, right? So single integral means area under curve, double integral, volume under a surface. Triple integrals we could not really visualize it. Right? However, if you take the integrand to be just one, right? So then this integral is basically actually just means the volume of the integration region. So triple integrals, when do we use it? Right, again, we use it when we consider the mass density or the center of mass. You could imagine if I again want to calculate the center of mass of this object, right? So then I have to do the triple integral. So here are some basic properties. Again, nothing would really be surprising to you, right? So actually, the first one, it just means that if you reverse the integral variable, right? So you still get the same result. Okay. And then the second one, right? Again, if I'm integrating the sum of two functions, I can just be equivalent to integrating each function individually and then add them up. And then finally, if this triple integral, if the integrand, okay, of this free variable can be written as a product of three functions, okay, and then each function only depends on one of the variables, then this triple integral can be written as the product of three one variable integral. So let's do this example and then we'll stop for today. So I'm using this temperature as an example. So I told you that I couldn't really visualize a function of three variables, but actually sometimes you can, right? So here you can just imagine that this is, suppose this box is our room, okay? So and then suppose I have this heater at one corner of this room, and then you can see that, of course, close to that corner, that room, then you have higher temperature. Okay, if you are far away, and then you have a lower and lower temperature. So then this is actually one way to represent a function of three variables without talking about the fourth dimension, right? So I just use different colors, right, to represent the value of the function at a particular point. Okay, so anyway, I'm considering this a cubic region, and then suppose my temperature distribution can be expressed by this function. I just make that up. Okay, so not really solving any physical equation to obtain this. I just make that up. So now, if I want to find out the average temperature of this region R, so what do I need to do? So what I need to do is actually just consider, right? Again, consider every tiny region dV of this room, right? So measure that temperature at that region, right, times dV, and then do it over again, and then divide this by the volume of the entire room. Okay. then that means I need to do this triple integral, okay, and then divide it by the volume of the room. So in principle, of course, the volume of the room is also can be written as triple integral, but here it's just, we know that it's just a box, right? Just a cube. So we know that. So then here the function is nice because it can be written as a product of three functions, right? The function of x only, the function of y only, and the function of z only. And that's why I just write this triple integral as a product of three integrals. Okay. And then at the end, I just get this number. So next time we'll continue with this triple integral. Okay, so in particular, you'll find that very useful is the case when we use cylindrical coordinates and spherical coordinates. Right? At least these two coordinates will be used very often in your E&M class. Okay. Okay, so we'll stop for today. Okay, remember the homework is still on this Saturday.